Yes, here, and we claim that here. It's okay. Take the n by n matrix and consider this system. We claim that a solution of our system is okay. Form a subspace. It's okay. If V is the set of the all solutions, so V is a subspace. Our aim is to show that V is a subspace. First of all, and V, and write V here. Let's prove to this one. It's okay. Consider AX is 0. It's okay. AX is 0. So, and the V contains x1, x2, xn, because A is n by n matrix or n by n matrix. It's okay. A is n by n matrix. It's okay. Matrix. Take this one, and in, of course, Rn, such that but and this vector x is okay, should be solution of this system. It's okay, not arbitrary vector, solution of the homogeneous system. So, and this one is in V. It's okay, and our aim is to show that V is not V is a subspace. So first one, V is, our aim is to show that V is empty set or not. So, and 0 here or not? Yes. And the zero vector in V, because what is the reason? Since, because, and the 0, x is 0, trivial, and the solution of the homogeneous system, x is 0, is a trivial solution of the system. Ax is 0, because what is the reason? A times 0 always 0, so x is a solution. X is 0 is a solution. It's okay. This one is a solution. So every solution in V, so 0 in V, 0 vector. It's okay. So, and V is not empty set. Yes, satisfy the person. The second one, take the two element in V. It's okay. Let x and y in V. So V contains all solutions of the system, and our aim is to show that x plus y in V or not. It's okay. That's one. This one. So, and x and y in V, what does it mean? V contains solutions of our system. So x and y in V means Ax is 0 and y is a solution of this system. Ay is 0. It's okay. So our aim is to show that x plus y in V, what does it mean? And it means, and the x plus y is a solution of the homogeneous system or not. It's okay. So, and take our matrix X, A, and multiply by x plus y. X plus y. So, and what's the this one? A is a matrix, X is a matrix, Y is a matrix. So, and this one is product, this one is addition. So, we know the distributivity used to this one, AX plus A sub Y. So, we know that under this one, AX is 0 and AY is 0 here. We use this one. So 0 vector plus 0 vector is 0. So we obtain, yes, we obtain A times X plus Y is 0. What does it mean? And means, and this one is a solution of our system, because coefficient matrix times this one is 0, homogeneous. So means, so, and we obtain X plus Y is a solution of the system. So, and the V contains all solutions. So means, yes, X plus Y in V. Is okay? Any question? So satisfy the and the second one, but and also sorry. And this one. You have to check the second one, second condition. Second condition, this one. And they take the one element here and they let x in V and take the any real number. Our aim is to show that R times X in V or not. It's okay. This one. So means, and what does it mean? And sorry, what does it mean? That is R times X is a solution. R times X is a solution of the R system means, and you have to check that Rx is 0 or not, is a solution of the system. So yes, let's look at the A times Rx and this one. Look at this one. A is a matrix, X is a matrix, R scalar. We know, and this one always we can write A times AX, R times AX. And also we know that, and here X in V and means A times X is a 0 because X is a solution. So, and R times, and use this one here. So R times 0 vector always 0. So we obtain, yes, A times Rx is 0. So what does it mean? And means, and Rx, that is, Rx is a solution of the system. So, and Rx in V because solution of the system. So, and the first one, second one, and the third one. So, and V is a subspace of Rn. So means, and let's come back our question. It's okay. And they take the homogeneous system and they find the all solution of the system. It's okay. Use a different color. So, and V is the set of all solutions of this system. This one is a subspace. This subspace is called the special subspace. Is called null space or solution space of A. This one, it is important space. It's okay. And they always take the n matrix. It's okay. And they find the solution space or null space of this matrix means construct this system, solve this system, and find the solution set. And we know that this fact, and the solution set is a space. This space is called solution space or null space of the matrix. It's okay. And denoted by this notation, N of A. Any question? Okay, no question. I think let's stop here because and not enough time here. It's okay. We will give the linear independent and the dependent vectors. And first of all, let's we have to give the definition of the linear combination, and we'll give some example. It's okay. And here, but and our aim here, the next in the next lecture is okay. And take the Rn, R space. It's okay. Contains and the vectors, and every vector here Rn, and every vector contains n components. It's okay. And the entries real numbers. It's okay. So, and for example, take the sum and the subset. Some subset is a subspace. It's okay. Some of them not subspace. Not, for example, 0 here. It's okay. And and sometimes, and the Rn contains infinitely many vectors. It's okay, Rn, for example, infinitely many vectors. But and they write the all vectors. It is not possible to write the all vectors. It's okay, but sometimes, and this one is a take the, for example, or Rn itself or any subspace of Rn. It's okay, and it contains infinitely many vectors. For example, look at the choose the one and the subspace here. Which one? This one is not subspace, and this one is a space. It's okay, subspace. This one is our space R cube. This one is a subspace V, for example. V is okay, and the V contains and infinitely many vectors. It is not possible to write to all of them. It's okay. So, but here I'll read, and here in the next lecture, choose the one and the set, one set, but finite. For example, contains and for example 3 vector only, and for example, and they say that this one is a B, set B, and if we know then this B is called the basis, and these for example contains 3 vector v1, v2, v3. It's okay. This one is, for example, take R cube. It's okay. And so it is possible to, for example, take here any vector here, or and here W, and every vector and can be obtained by using the these and the 3 vector. It's okay. You don't have to write all of them. If we know the v1, v2, v3, it is possible to compute the all vectors. It's okay. So we know every vector because and every vector is generated by using the v1, v2, v3. So and this one is spatial vectors. It's okay. This set is called the basis because generate the all space. It's okay. This one. But this set contains only 3 vectors, but it is possible to get the infinitely many vectors and the all vectors in our space. It's okay. So, and this concept, it is important. It's okay. Now let's stop here, and so next day we will give this concept. It's okay. Any question about the